Hi, my name is Andrej Obuljen and I'm a postdoc at the University of Waterloo. I would first like to thank the organizers for giving me the opportunity to talk. I'm very excited to tell you about the detection of anisotropic assembly bias in BOSS Galaxies. This is a work I did in collaboration with Will Percival and Ian Dalal. And in the bottom, I show you two references to the papers I'm going to discuss. So let me just start from with an outline. I'm going to give you a brief introduction. Then I'm going to tell you about what we mean by this anisotropic assembly bias and how it manifests itself in simulations. Then I'm going to show you how we detected this galaxy anisotropic assembly bias in BOSS galaxies. Finally, I'm going to show you some other consequences and summarize at the end. So we are at this exciting stage where we have this very successful lambda CDM model that describes a lot of things in the universe. And we'll get this information from many different observables. However, the inhomogeneities have been the dominant source, mainly through the two-point statistics of all these density or temperature fluctuations. So for example, the prime example is the CMB measurements, which still dominate the constraints on most of the cosmological parameters. However, large-scale structure is kind of creeping in. So like since it's a three-dimensional observation, it's expected to ultimately have more constraining power than the CMB. So by probing bigger volumes of the universe, upcoming galaxy redshift surveys like LOWZ and Euclid hope to reach unprecedented precision on most of these cosmological parameters. However, this comes with a price, with all the neglected observational theoretical systematics kind of showing up at this level of precision. So what are we really trying to do in large-scale structure is basically we're trying to infer the matter power spectrum. So the matter power spectrum is defined as this two-point function of the matter over density field, and in principle it's a function of the wave number vector. However, since we assume that the universe on large scales is homogeneous and isotropic, this matter power spectrum depends only on the amplitude of the wave number. And for example, here I'm showing the matter power spectrum reconstructed from various different observables, showing great agreement between different observables. However, this is not an easy task. So and this basically comes down to that we neither observe the dark matter nor we observe the real space positions of galaxies or other traces. So what do we really observe? So we observe the bias traces of matter, for example, galaxies, halos, voids, 21 centimeter Lyman alpha forest, and we don't observe them in real space, we observe them in redshift space. So to start off, there is a relation between the observed overdensity of galaxies and matter overdensity. And these are on very large scales described by a very simple linear scalar bias, this BG, for example, for galaxies, which basically scales the amplitude of the observed power spectrum with respect to the matter power spectrum. This scalar bias depends on halo mass and redshift, so massive objects are more biased, and objects earlier on are more biased. So there are these two dependencies. However, as I said, on top of this, we observe tracers of matter in redshift space. So they suffer from these redshift space distortions, which makes them being more, which amplifies the clustering in the radial direction. So this is well described on very large scales in linear theory by this Kaiser form. Basically, the overdensity field in redshift space of matter is amplified in the radial direction by this term mu squared, where this f is the growth rate and mu is the angle with respect to the line of sight. Assuming that on large scales, velocities of any tracer you pick up and the matter, they fall within the same velocities, means that there is no velocity bias. So that when you observe your galaxies, the only bias, galaxy bias, shows up in here and not in this redshift space distortion term. So this is kind of known and standard. So in linear theory, what you really observe is something like this. So your power spectrum that was 1D in real space and for matter now becomes a 2D power spectrum. So so now you need to decompose it or And usually this is done using the Legendre expansion. So you decompose it into multiples, and we usually only focus on the monopole and the quadrupole. So the monopole tells you about some mean amplitude of the observed power spectrum, while the quadrupole tells you about the anisotropy of this power spectrum. So for example, there's a cartoon picture here. In real space, the power spectrum is isotropic. In redshift space, it's anisotropic. There is a squashing in the radial direction. So if you measure the power spectrum, the monopole and quadrupole, you can actually measure both the bias and the growth rate. And also know that in the absence of redshift space distortions, there is no quadrupole, and it's directly proportional to this to the growth rate. So this is exactly what we also see in data. So this is real data to the power spectrum. So why are we interested in all of this, and why should we care so much about these measurements? Well, we really want to pinpoint this growth rate since it's one of the key parameters. So this growth rate is defined as the logarithmic derivative of the scale factor with respect to of the growth factor with respect to the scale factor. And this in GR we have a prediction for it, and so testing it across various redshifts is very important for testing gravity, constraining neutrino masses, and so on. So currently we are at the level where we know this, we have measurements of this parameter up to 5 to 10%. But future surveys, for example, DESI and Euclid, are expected to reach 1 to 5% precision. So any systematic that could show up there when these error bars go down, it's very important to take into account now rather than later. On top of all of these, as I said, this assembly, the standard galaxy bias depends on mainly on the mass, halo mass, and redshift. However, if you look more detail, once you fix the halo mass and redshift, halos show other dependencies on their scalar intrinsic properties, for example, age, spin, concentration, shape, and so on. And so this effect is very hard actually to detect in data, since you need to be sure that the objects you're observing have fixed halo mass. This is rather difficult in real observations. However, this has been detected in simulations, and so I just wanted to have this in mind. This is the scalar assembly bias. Now, if we move on to non-scalar bias, now the picture becomes a bit more complicated, but we are still at the linear level in overdensity field. So we usually assume that there are only these two terms that are linearly on overdensity field. However, there's another term that's also linear on overdensity field, and that's the traceless part of the tidal field, given by this equation here. So now how it enters the observed overdensity field is like this, and you can immediately see that the scalars cannot correlate with the tidal field. So only non-scalar properties can, and actually they do. So for example, we measure this cross correlation of various non-scalar halo properties with tidal fields, and they correlate with tidal field on all scales, basically. So now if we only focus on the radial component of this non-scalar bias and assume that halos look the same in the plane of the sky, however you orient them, and you call this ZZ component BQ, then you end up with an equation like this. And the reason why we call this BZZ BQ is because it has this exactly the same shape as the quadrupole, right? So this has all been known before. This has been pointed out in the literature for more than 10 years now. So this is kind of an interesting effect now, because from something that looks like this, very simple, now we have a bit more complicated form where the bias is modified, but also the growth rate has this other term. And so this BQ is really what we call anisotropic assembly bias. It is a source of anisotropy in the real space power spectrum, and it adds only to the anisotropy in redshift space, and it's completely degenerate with F. So you can imagine that this could be a problem when measuring the F from galaxy redshift surveys, because in particular you will not be measuring F, you will be measuring F plus BQ. Now, why is this BQ usually assumed to be 0? So there are two ways for it to be zero. And one way is that, as we shown, halos do correlate with tidal fields. So the only way this could be zero if your selection is independent of halo orientation. So for example, if you're choosing all halos irrespectively of their projected size, velocity, dispersion, angular momentum, and so on. Or if you cannot satisfy that, maybe your observed tracer and its host halo are randomly misaligned. If this is satisfied, there is no need to worry about this effect. This BQ is basically zero. However, it's very hard to be sure about any of these. And so that is the big problem. So in order to show you how big this effect can be, what I'm doing here is I'm splitting halos in a galaxy based on their tensor properties, in particular based on their radial extent and their 1D velocity dispersion. So one set of halos are aligned with my line of sight, and one set of halos are are perpendicular to the line of sight. So I'm in real space, so there are no redshift-space distortions. So I'm expecting that my quadrupoles of these guys to be zero. If they're not, the only way this could happen is that this BQ is different from zero. And if I do measure, I get a very non-zero quadrupole. And basically on all scales, so this is the worrisome effect, that in real space, the quadrupole is very non-zero. And if you look at the difference of this anisotropic assembly bias between the two subsamples, this can be of the order of 1 or 2, which is a problem because what you're trying to measure, the growth rate, is of the order of 0.7. So you need to be sure that this BQ is 0 to very high precision. And that was fine. That was for real galaxies. And that was for halos in simulations, sorry. So we were wondering, what about real galaxies? So there is this big step from halos to galaxies because halos may not be very aligned with halos. So what we were wondering is like, what happens if we split based on orientation dependent quantities? Do galaxies show different clustering strength as halos did? And so we looked at BOSS DR12 galaxy sample, which is made up of mainly of these luminous red galaxies, which are elliptical galaxies, which have been shown before to be aligned to some degree with their host halos. So how do we look for this anisotropic assembly bias? Well, in the same way that we looked in simulations, similar way. So our main idea is to split on something that depends on orientation, in this case, the velocity dispersion, 1D velocity dispersion, and to look for differences in the anisotropy. So our null hypothesis is that this effect is not present in our subsamples, okay? So that the difference is also not present. So what do we do? So we say, okay, if we have subsamples that match the redshift distribution, they must have matching growth rate. Also, these subsamples can have different biases and different assembly biases. But if we find subsamples that have matching monopoles and redshift distribution, then any mismatch in quadrupoles is an evidence that this delta BQ is different than zero. So, so how do we proceed? So we need some galaxy orientation dependent galaxy property. And we use these velocity dispersion measurements and stellar mass measurements from the Portsmouth group. This is how they look like, for example, for CMASS. This one big blob, which has all these redshift dependencies and so on. So you could naively split on the velocity dispersion, right? You take high velocity dispersion, low velocity dispersion. However, this is not really just a split on orientation. This is also a split on galaxy mass, since the velocity dispersion scales with the galaxy mass. Hence, this is also a split on galaxy bias. So, but we can use the stellar mass, the measured stellar masses, to remove this dependence. And we can make subsamples that either have high stellar masses and low velocity dispersion, or vice versa. So, and here are these two subsamples shown. So one of these subsamples is the blue one. It has high velocity dispersion and low stellar masses, and vice versa for the pink one. So then we tune these cuts such that we match the monopoles. And these are the results I'm showing here. So for example, for CMASS, I'm showing you here that these two subsamples that we pick up are shown in these pink and blue curves compared to the full sample scaled to the number of the galaxies in the subsamples, so 25%. So they match rather well on all redshifts. On the right, I'm showing you the measurements of the multiples. So on the top ones, you have monopoles of the two subsamples. They match rather well on all scales. However, and this is what we were trying to find, is that when you do this, when you match monopoles, you find different quadrupoles, and they are significantly different on all scales. And this is also true for LOWZ. So for LOWZ, it's a bit different, the redshift distribution, but the main argument stays. So in order to test the significance of this, we can use mocks. So for example, in mocks, mocks don't have this effect, right? So by splitting each mock into two random subsamples, we can make many realizations of how much monopoles can match and how much quadrupoles should match within the error bars. And then look if our results are deviating from that. So we did that, and we show basically that while our monopoles match within 1 sigma on all scales, we find different quadrupoles, so many sigmas away, as soon as we get to Kmax of 0.1 or 0.15. This is true for both CMASS and for LOWZ. And so once we have that, so once again, our main null hypothesis is that there is no, that this effect is not present. If it's not present, matching redshift distributions and monopoles should give you same quadrupoles. So here we are basically making a statement about our quadrupoles being different and what is the significance of this. And so here I'm showing that you individually from LOWZ and CMASS, you get at 0.15, you get to 3 sigma detection. And if you combine them, since they're independent, you get 5 sigma at 0.15. Right, so yeah, so let me just make a little break here, a little discussion. So we present significant evidence of anisotropic assembly bias in BOSS galaxies. Basically, we have shown that the clustering of galaxies depends on local properties that are not halo mass only. And our detection is actually the first one to exceed the level of 5 sigma. So we are excited about this. You should know that we only measure the delta BQ, the difference between two subsamples, not the full subsample BQ. So it is not to worry that these results show that the BOSS sample is biased at this degree. But for BOSS galaxies in particular, we do find subsamples that have delta BQ between the two subsamples of the order of 0.1, 0.2, while for halos in simulations, we have found before subsamples that can have even of the order of 1 or 2 for similar halo masses. This is not so unexpected, since you expect that there is some misalignment of galaxies and halos, which will of course decrease the signal. Now, there are other consequences one should keep in mind, right? So this is kind of a orientation-dependent selection effect that if your tracer is coupled with correlated with the tidal field, it will show up in many other ways. So for example, emission line galaxies that DESIs will be the main sample of the DESI survey, they contain dust, so maybe the target selection is sensitive to orientation. Then, of course, one should keep in mind that whether ELGs are at all aligned with halos, there is still not any detection of this alignment. Other consequences, for example, groups, clusters found in redshift space, they exhibit strong anisotropic assembly bias in the clustering. And also it could be an issue for redshift space distortions with 21 centimeter intensity mapping due to H1 self-absorption for the same reason as for the galaxies. And other ones. So just to summarize, we find this anisotropic assembly bias in clustering of halos, both in numerical simulations and in clustering of real observed BOSS galaxies. This anisotropic assembly bias is caused by correlation of large-scale tidal fields and non-scalar halo properties. And contrary to the isotropic assembly bias, this effect cannot be mimicked by varying halo mass. And one should be careful about all these orientation-dependent selection effects of halos, because they can produce anisotropic power spectrum even in real space. But in redshift space, they are degenerate with the growth rate, and so care must be taken when interpreting these RSD measurements. Thank you very much for listening, and I'm looking forward to discussing with you. Bye.